one of the topics of use case or applications of the 5G and the networks and help these V2X scenarios is edge computing. So, and then we thought that how could we address mobility and edge computing? So in this particular case, so there is a truck trying to point to, you can see it, okay. So in this case, a truck is leaving a private network, in this case a PNI, so a public network integrated non-public network. So it's a slicing operator. So this truck leaves this entity, then crosses the public network, and then its objective is to reach a standalone NPN. So a 5G network instantiated totally in a private domain. So we have the public network with several runs or tracking area codes, simplified by different ALBs, by different runs. Each run is connected to UPF, and each UPF is connected to an edge computing platform to run as closest as possible application services. And then we have on the top the 5G core and the central cloud of the operator. So this truck is moving, so goes from right to left, and when handovering from run to run, the idea is that it is served from the closest edge computing node. So these edge computing nodes are distributed along that path. So while moving the trucks or the vehicles, in this case, is truck handovers. So since the handovers, at least to reach the closest one, if nothing is done, so the service is reachable through a different IP. And in fact, that's not so simple because we also need, so if it was a normal network, a central UPF would be used, and without this feature of 5G, that is this service and session continuity mode 3, though this feature on 5G standalone, so allows anchor point of a session to change point of attachment. So it allows the PDU session established between the truck and a UPF. So when moving, to change that anchor point to another UPF. So it's a feature that was specified and designed implementation of 5G just to allow some mobility and this kind of edge computing. But that's not all. So something must be done. So the network must implement this feature, this service and session continuity mode 3, so that allows this session mobility inside the network. But with that, IPs change. So we changed the IP address of the moving terminal, the user equipment that is now, in that case, in the truck, and also the services change IP if nothing is done. So, and then connections are established, etc. If the service is reached, identified by its name, so different IPs represent different names, but the terminals are not always requesting a name resolution on the DNS, so it resolves the first time, then for a certain time it doesn't resolve again. So these will not work if nothing is done. So in a very simplified way, what we have done, so we have made changes in a set of components of the network. So, and we decided that this is the right approach. So we have a global name for the service. So the service has a global name that is known everywhere, that is converted in an IP address when this conversion is requested to convert the service name into an IP. So that DNS record is created in the central DNS. That IP that is returned, it doesn't exist on the network. It is a virtual IP that is assigned nowhere, in no place. For the service to work also, so when deploying the service instances are deployed and started at each different edge computing node. So different IPs exist associated to the platform or to the application, but in every location, the IP to reach the service is different. So what we have done, we have changed this UPF function to have NAT functions. So in fact, what we do, so we convert the global IP that is never assigned to no entity. So in each UPF, it is translated to the right IP that this application, that application instance has in each edge node. So with that, when the truck is moving, so the IP is seen, the service IP is seen from its location, always with the same IP. So when sending packets to that IP, so the packets are sent to a destination, and then in UPF, there are some rules that say that this IP should be translated into a locally served IP that corresponds to the IP service or that specific application instance running in the closest, and closest may mean many things, in this case geographically closed to the user equipment, to the truck location, and so it is served that way. So this minimizes, at the same time, minimizes the latency, distributes traffic, so the clients are always best served. So this is in a very generic way, the way we implemented it and the way we demonstrated it. For this, we have the tool that we used is Open5GS, so this open core, open source implementation. We also used the UPG travel ping, so it is a UPF implementation outside Open5GS. So it's one that is implemented in VPP. And we changed it, for instance, to improve that NAT functions that already existed, but not operating in the way we wanted them to operate. Since we didn't have so many runs available, so here in Nautilus Labs we have a private 5G network, but with a single run, a single GNodeB. So we don't have enough GNodeBs to test this in reality. So we use these UE run sims that many of you know to implement those different GNodeBs connected to the core. And we used an open source implementation of an edge computing platform that is Edge Gallery. And we also had to modify it. So Edge Gallery, it's an open source tool. It is backed by many Chinese and Indian entities, also some Occidental entities already working on it, like IT in Aveiro. So we knew about it, so we deployed it, and this is as a common edge computing platform with a central node and an edge node. So from the central node, you can upload workloads, and then through the graphical user interface of Edge Gallery, so we decide in which edges the workloads are deployed, and so you manage which workloads will operate in each edge node. So we used it with a central node, or 3 edge nodes, and we made that changes. So we corrected some issues with Open5GS code related to tracking area codes. So in fact, each GNodeB is a tracking area code. We modified Edge Gallery to integrate with 5G plane. It already integrates with it, but not the way we wanted it. There are some different rules in the way we wanted it. So Edge Gallery has that advantage. It's different from the other edge platforms, the computing platforms that they don't integrate natively with 5G. Edge Gallery has that feature, so it has already the MP2 interface that EdCMEC specified. It is implemented by Edge Gallery, so that was also one of the arguments for us to check this. So it has these native integrations, but not operating as we wanted, so we changed it. We added or changed the way the central DNS works in Edge Gallery. So to return that global IP, we modified the travel ping UPG, the UPF, to receive those traffic rules. And then to demonstrate it, we also developed a video streaming server application to be used and to demonstrate the features. So in our case, so the truck is moving or simulate is movement, and then it is receiving a video stream that changes. The content is different in a transparent way when it moves from point of attachment to another point of attachment. Well, to have more details on the YouTube channel, we have uploaded a demo, a video regarding this demo, where in a very detailed way, this is explained.